Section 1.6, Solving Trig Equations with Calculators, Part 2. As with the last few examples we saw from the previous section, we are not going to be looking for solutions in an interval in order to save space. The important part of these examples is to find the solutions to the equation. If we'd been given an interval, it would be easy enough to find the solutions that actually fall in the interval. In all the examples in the previous section, all the arguments, the 3 times t, alpha divided by 7, etc. were fairly simple. Let's take a look at an example that has a slightly more complicated looking argument. Example 1, we're going to solve 5 times the cosine of 2x minus 1, which is equal to negative 3. Note that the argument here is not really all that complicated, but the addition of the minus 1 often seems to confuse people, so we need to do a quick example with this kind of argument. The solution process is identical to all the problems we've done to this point, so we won't be putting in much explanation. Now, here is the solution. We have 5 times the cosine of 2x minus 1 equals negative 3, so the first thing we have to do is divide by 5. Now we have the cosine of 2x minus 1, which is equal to negative 3 over 5. Then we're going to divide by the cosine to then get 2x minus 1 is equal to the cosine inverse of negative 3/5. Well, now, the cosine inverse of negative 3/5 is equal to 2.2143. So we have 2x minus 1, which is equal to 2.2143. Now, the angle is in the second quadrant, and so we can use either negative 2.2143, or we can take 2 pi minus 2.2143, which is equal to 4.0689 for the second angle. As usual, for these notes, we'll use the positive one. Therefore, the two angles are the following. We have 2x minus 1, which is equal to 2.2143 plus 2 pi n, 2x minus 1, which is equal to 4.0689 plus 2 pi n. Now we need to solve this equation as if we're going to isolate x. So when you isolate x, recall that you're going to have to add 1 and then divide by 2. Now, we still need to find the actual values of x, like I just stated, that are solutions. They are found in the same manner as all the problems above. We'll first add 1 to both sides and then divide by 2. And doing this now gives us x, which is equal to 1.6072 plus pi n. X is equal to 2.5345 plus pi n, when n is equal to 0, plus or minus 1, plus or minus 2, and so on. So in this example, we saw an argument that was a little different from those seen previously, but not all that different when it comes to working the problems. So don't get too excited about it. Now we need to move into a different type of trig equation. All of the trig equations solved to this point, the previous example as well as the previous section, were in some way more or less the standard trig equation that is usually solved in a trig class. There are other types of equations involving trig functions, however, that we need to take a quick look at. So the remaining examples show some of these different kinds of trig equations. Example 2, we want to solve 2 times the cosine of 6y plus 11 times the cosine of 6y times the sine of 3y, which is equal to 0. So this definitely doesn't look like any of the equations we've solved to this point, and initially the process is different as well. First, notice that there is a cosine of 6y in each term. So let's factor that out and see what we have. So if we factor out the cosine of 6y, what's left is 2 plus 11 times the sine of 3y, which is equal to 0. And now we're going to use the zero product rule. So we now have a product of two terms that is 0, and so we know that we must have cosine of 6y, which is equal to 0, or 2 plus 11 times the sine of 3y, which is equal to 0. So now at this point, we have two trig equations to solve, and each is identical to the type of equation we were solving earlier. Because of this, we won't put in much detail about solving these two equations. So in here, we have, first we're solving cosine of 6y is equal to 0. So we get 6y, which is equal to pi over 2 plus 2 times the pi n. 6y is equal to 3 pi over 2 plus 2 pi n. Now, dividing both sides by 6, we get y, which is equal to pi over 12 plus pi n over 3. Y is equal to pi over 4 plus pi n over 3. Now next we want to solve 2 plus 11 sine of 3y, which is equal to 0. So what we're going to do here is we're going to end up getting 3y, which is equal to 6.1004 plus 2 pi n, 3y, which is equal to 3.3244 plus 2 pi n, to give us the following. Y is equal to 2.0335 plus 2 pi n over 3, and y is equal to 1.1081 plus 2 pi n over 3. Remember that in these notes, we tend to take positive angles, and so the first solution here is in fact 2 pi minus 0.1828, where our calculator gave us negative 0.1828 as the answer when using the inverse sine function. So the solutions to this equation are then y, which is equal to pi over 12 plus pi n over 3, y is equal to pi over 4 plus pi n over 3. So y is equal to 2.0335 plus 2 pi n over 3, and y is equal to 1.1081 plus 2 pi n over 3, provided that n is equal to the following. Now, this next example also involves factoring trig equations, but in a slightly different manner than the previous example. Example 3, we're going to solve 4 times the sine squared of t over 3 minus 3 times the sine of t over 3 is equal to 1. Before solving this equation, let's solve an apparently unrelated equation. If we had 4x squared minus 3x equals 1, we would subtract a 1 to the left side and then factor. So we get 4x plus 1 times x minus 1, which is equal to 0, and then we would get x, which is equal to negative 1/4 and 1. This is an easy, or at least we hope it's easy at this point, equation to solve. The obvious question then is, why did we do this? Well, if you compare the two equations, you'll see that the only real difference is that the one we just solved has an x everywhere, and the equation we want to solve has a sign. What this tells us is that we can work the two equations in exactly the same way. We will first factor the equation as follows. So we have 4 sine squared t over 3 minus 3 sine of t over 3 minus 1. So we're going to factor this now to be 4 sine of t over 3 plus 1 and sine of t over 3 minus 1, which is equal to 0. And then we're going to set both of these equal to 0. So the first one, if we let 4 sine of t over 3 plus 1 equals 0, we're going to subtract 1 to both sides and then divide by 4. So we get sine of t over 3, which is equal to negative 1/4. Over here, we add 1 to both sides, so we get sine of t over 3, which is equal to 1. So now what we have are two trig equations that we can easily and hopefully solve at this point. We'll leave the details to you to verify that the solutions to each of these, and hence the solutions to the original equation, are t, which is equal to 18.0915 plus 6 pi n, and t is equal to 10.1829 plus 6 pi n, and t is equal to 3 pi over 2 plus 6 pi n. The first two solutions are from the first equation, and the third is from the second equation. Let's work one more trig equation that involves solving a quadratic equation. However, this time, unlike the previous example, this one won't factor, and so we will need to use the quadratic formula. For example 4, we're going to solve 8 times the cosine squared of 1 minus x plus 13 times the cosine of 1 minus x minus 5 equals 0. Now, as mentioned prior to starting the example, this quadratic does not factor. However, that doesn't mean all is lost. We can solve the following equation with the quadratic formula. So hopefully you remember this and how to do that. So you have 8t squared plus 13t minus 5, which is equal to 0. Using the quadratic formula, we end up with t, which is equal to negative 13 plus or minus the square root of 329 over 16, which is equal to 0.3211 and negative 1.9461. So if we can use this quadratic formula on this, then we can also use it on the equation we're asked to solve. So doing this, we know that the cosine of 1 minus x is going to equal one of the solutions to be 0.3211, or the other one is going to be cosine of 1 minus x, which is equal to negative 1.9461. 0.9461. Now recall that from example 9 from the previous section, in that example we noted that cosine theta has to be in between -1 and 1. And so the second equation will have no solutions because this is beyond the -1. Therefore, the solutions to the first equation will yield only the solutions to our original equation. Solving this gives us the following set of solutions. X is going to equal -0.2439 minus 2 pi n, and x is going to equal -4.0393 minus 2 pi n. Now note that we did get some negative numbers here, and that does seem to violate the general form that we've been using in most of these examples. However, in this case, the negative are coming about when we solve for x after computing the inverse cosine in our calculator. There's one more example in this section that we need to work that illustrates another way in which factoring can arise in solving trig equations. This equation is also the one where the variable appears both inside and outside of the trig equation. Not all equations in this form can be easily solved, however some can, so we want to do a quick example of one. Example 5, we're going to solve 5 times x, or 5x times the tangent of 8x, which is equal to 3x. Now first, before we even start solving, we need to make one thing clear. Do not cancel an x from both sides. While this may seem like a natural thing to do, it will cause us to lose a solution here. So, to solve this equation, we'll first get all the terms on one side of the equation and then factor an x out of the equation. So if we can cancel an x from all the terms, then it can be factored out. So doing this, we have 5x times the tangent of 8x, and we subtracted 3x to both sides. And now what we can do is, since both of these terms have an x involved, we can factor out an x. So we have x times 5 times the tangent of 8x minus 3, which is equal to 0. So now we can set this x equal to 0, and we can set this tangent 8x, which is equal to 3/5, because we add 3 to both sides and then divide by 5. So now we have these two scenarios. Now note that if we cancel the x, we would have missed the first solution. Now we solved an equation with a tangent in it in example 5 of the previous section, so we'll not go into the details of the solution here. Here's the solution to the trig equation. So for this equation, we got x, which is equal to 0.0676 plus pi n over 4, and x is equal to 0.4603 plus pi n over 4. And then the complete set of the solutions then to the original equation are the following. X is equal to 0, and then those two that we just mentioned.